Okay, I'm waiting for a couple of minutes. I will start after that. I'm waiting so that people can join. I will start after 2 3 minutes. Okay. So about the question paper, I have no idea, but only thing I can say that it will be similar to the assignment questions and the problems that we solve in the live sessions. Those will be helpful. If you have like other question, you can write in the discussion forum in that Shwayam portal. uh, like people, I'm not the right person to answer this type of question. If you have any exam related question, then you can post there. One of the team members will respond to you. I think we can start. People can join. Okay. So, good afternoon. Welcome to the live session for the course Sensor Technologies, Physics, Fabrication and Circuits. This is week 8, so we have covered the topics those were discussed and problems related to those topics from week 1 to week 7. So, this is the last week. Let me start the session by introducing myself first. I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI. So I will be your TA for the session. So the purpose of this session is to solve questions, and also I try to give a brief summary of the topics those were covered in this week, so in every week before starting the problem solving part. Okay. So in this week, this course has three components: physics, fabrication and circuits. So this week was about circuits part, like different types of circuits associated with sensors. Sensors can be of any type, but most sensors are electronic or electrical sensors. The output is electrical signal. So that is why we discuss different interfacing circuits. Now, to make a system out of a sensor, we need certain circuitry apart from the sensor. Also, sometimes to make the sensor output readable, like readable that means so that it makes sense to the common people. For that also we need some circuitry. Say it will display some number, it will it will give some output that by which the common person will get get notification, and gives an indication that what the sensor output actually means. So let's start the session. So first topic that was discussed was sensor system. So I hope that you all have gone through the lecture videos. So what is a sensor system? So the block diagram of a sensor system is, so that you will have a sensor. The output of the sensor you will feed to a signal conditioning circuit. So this is signal conditioning circuit. What are different components in the signal conditioning circuit? First is filter. Will filter out the actual output signal, and then amplifier. If the output of the sensor is low, say it gives a output signal in microvolt or microampere range, it may not be readable by your measuring system. So we typically need an amplifier, and before that we filter out the output signal, actual output signal. Why the filter is kept before the amplifier? Because if there is any noise signal in the output, so if we keep amplifier first, that will also be amplified. So we filter out the signal we want, that gives us some information, and then we amplify that signal. So after this signal conditioning part, what we typically have an ADC, analog to digital converter. As I mentioned, most sensors are electronic in nature, and so to do some decision, we typically use an analog to digital converter, because I mentioned in earlier classes also, using an ADC we can convert a analog signal, say 0 to 5 volt, to a we can assign different numbers, say 0 to 255. So 255, so this is like a digital conversion, the decimal equivalent of the binary number, and we can assign different range, say 0 to 60. For it will indicate something, then 65 to say 125 it will indicate something, and say 126 to 255 it will indicate something else, maybe high, medium, low, some indication it will give. Now after this conversion, we typically have a processor, and after that memory or display element. So this is a complete sensor system. So a processor, some microprocessor, maybe you have made some circuit using Arduino board or similar kind of microprocessor IC, in Arduino board also there is an IC that performs the processing part. So this is a sensor system. So the output of the processor we can display, it can be stored, or it can be given to an actuator to do some work. An actuator can be like a motor. So based on your sensor output, say you want to turn on a motor or turn off a motor, so you can, based on the decision taken by the microprocessor, that actuator can be controlled. So this is a typical sensor system. So this part is not always necessary. The ADC, sensor and memory and display, it can be different depending on your system. So we focus on the signal conditioning circuit part. So these are typically two components we have filter and amplifier, and in this week filter and amplifier, those topics were discussed. Next, the second topic that was covered in this week was voltage divider circuit. So what is a voltage divider circuit? So we apply a voltage, say V1 or V in, let's say, across these two nodes, and there can be like two resistors, can be more than two also. This is R1 and R2, and if we measure voltage across this second resistor, say this is V2, and voltage across this first resistor is say V1, then what is V2? V2 is equal to R2 by R1 plus R2 into V in. So this is a very basic circuit that we studied in our B.Tech level and even before also, that can divide input voltage into different voltage based on the resistance values. Now, why we discussed a voltage divider circuit, in many cases our sensors can be resistive type. So instead of the sensor, we can this resistor, we can place our sensor and we can measure the voltage across the sensor. That can give indication about the change in resistance, because if the resistance changes, voltage across the resistor will also change, voltage across the sensor also change, and we can correlate with it with the input signal. So this was the first circuit that we discussed. Next one was Weston bridge circuit. So what is a Weston bridge circuit? So my diagram is, I hope, clear. So this is a Weston bridge. Say this is V in. This resistor is R1, R2, R3, R4, and the voltage here is, say this is node A and this is node B. So this voltage is VAB. So this is a Weston bridge circuit, and we know from our previous knowledge is that the bridge is balanced if R1 by R2 is equal to R3 by R4. So how we can get that? So we use again voltage divider circuit, voltage division rule. So voltage here at this node VA, that will be equal to R2 by R1 plus R2 into V in, because this V in is across this R1 and R2. Similarly, VB is equal to R4 by R3 plus R4 into V in. So VAB will be the difference, which is VA minus VB, which is equal to R2 by R1 plus R2 minus R4 by R3 plus R4 into V in. Now we call the bridge is balanced. That means there is no voltage between node A and B. VAB is equal to 0. When VAB is equal to 0. So VAB is equal to 0 means so V in is not non-zero, we are applying some voltage, so this part will be 0. So R2 by R1 plus R2 is equal to R4 by R3 plus R4, and if we do simplification of this expression, we will get R1 by R2 is equal to R3 by R4. So this is the balanced condition for Western wheels. Next topic was amplifier. So we have seen the amplification using an op-amp, operational amplifier. So this is the circuit diagram for an op-amp. So there is one non-inverting terminal, there is one inverting terminal, and there is this output terminal. There is V plus and V minus. These are supply voltage, because this is an IC. The whole circuit is inside an IC, and to operate an IC we have to apply some voltage to it. So that supply voltage is given as V plus and V minus. But this is the for op-amp the circuit number is IC741. Maybe you have done some experiment in UZ level with IC741. So this is the pin diagram. So this inverting input is 3, so this is 3, and non-inverting, so non-inverting is 3, inverting is 2, minus supply voltage is 4, and plus supply voltage is 7, and 6 is output. Okay, so we make these connections while making a circuit using IC 741. In an IC 741, that is in case of an op-amp, so operational amplifier, the output voltage is given by this formula, OL, V2 minus V1, voltage at the inverting terminal minus V1, and this is known as open loop gain. Now in case of op-amp, open loop gain is very high, so we don't operate an op-amp using an open loop configuration. We use feedback, we give negative feedback so that we get a stable output. Now like you must have some course in your UC level where you have studied about op-amp. So in analog circuit there are different circuits using an op-amp, and what is inside of an op-amp. So it's a very vast subject. So in this course, so this is not a circuit or analog circuit course, so only an overview was given, and I will also try to give like a simple summary of whatever the overview that was given in this week. Is there any question? Marking. So you can so you have one Q&A tab in the Zoyan portal. You can ask the question there, because I am not in that team, so I'm not dealing with any exam related things. I'm not so there are other people who can help you out. You can post your question, they will answer. The only thing I can say that the question will be similar to the ones that we are discussing, and those were given in the assignment also. Okay, so you can ask there. I'm not aware of the exam pattern or anything. So in op-amp, how an op-amp can be used as an amplifier. So there are different configurations. First one is non-inverting amplifier. So in non-inverting amplifier, this is the op-amp, this in non-inverting terminal, inverting terminal. Voltage is applied in the non-inverting terminal, and in the a feedback, negative feedback is connected here. So this is R1, this is R2, and this is the output pin, that is pin 6. So this is the configuration of a non-inverting amplifier. Now how we solve this circuit? First of all, we take two consideration, that input impedance of an op-amp is very high. So if you know about the internal circuit of an op-amp, so you will know that input impedance of an op-amp is very high. So Z in for this circuit is very high. So there is no current flowing inside here, and another consideration we take that comes from it is that voltage as inverting terminal and voltage at non-inverting terminal, these two are same. So V plus is equal to V minus. Okay. Now in this case, V plus is equal to V in, right? So this voltage is also V in at this node. So say there is a current flowing through it like this, I. So I is equal to, so current will be, we can use KVL in this loop. So V out by R1 plus R2. Similarly, we can consider this node and we can apply KVL in this loop. So we can say that I is equal to this voltage at this point, which is equal to V in by R1. So V out is equal to, so these two are same, V out by R1 plus R2 is equal to V in by R1. So that means V out is equal to 1 plus R2 by R1 into V in. So we know that the relation between output and input, that is the like the gain, the ratio of output voltage and input voltage, that is the gain for a circuit. So in this case, the gain is 1 plus R2 by R1. So we can adjust the R1 and R2 value so that we get like desired gain for this amplification, like desired amplification. Okay. So this is gain. Next configuration is inverting amplifier. So in inverting amplifier, we apply the input signal to the inverting terminal. So this is minus, plus, this is grounded, the non-inverting terminal is grounded. This is R1. Here we apply the input voltage. Remember, this V in can be a digital signal, it can be an analog signal also. This is R2 and this is V out. Okay. So we are applying this negative feedback for stability. So again, this is V plus, this is V minus, and we consider for op-amp input impedance is very high, that means it does not draw any current, and the points here, like the inverting terminal and non-inverting terminal, the potential are same. So V minus is equal to V plus. So here V plus is 0, so V minus is also 0. So we can consider a current here which is like this, I. So I is equal to, say, we can consider here V in minus V minus V minus by R1, and we know that because these two are virtually ground, so V plus is 0, that means V minus is also 0, so this is V in by R1. Next I we can consider from here to here. So this is V minus V out divided by R2 again. So V plus is equal to V minus, which is equal to 0. So this is 0. So I is equal to minus V out by R2. So this current and this current is same because that is the same current flowing through it. So V in by R2 R1 is equal to minus V out by R2. So V out is equal to minus R2 by R1 into V in. So in this case gain is equal to minus R2 by R1, and because we are applying our signal to inverting terminal, our gain is this. The amplification is happening but the signal is inverted, and in this case for non-inverting amplifier the gain is positive. That means we are getting amplification but the signal has the similar amplitude as the input signal. Okay, so this is about inverting and non-inverting terminal. Next topic that was discussed, next circuit we can see differential amplifier. So in differential amplifier we apply signal to both the non-inverting and inverting terminals. So the configuration is like this. We apply one voltage V1 here, say this is V plus, this one is R1, this is R2, and we apply another signal here. Again we will apply negative feedback. So this is R2, this is the second applied voltage, so this is V2, this is R3, see. And this is the feedback resistor R4, and we have this output V out. Okay, this is V minus. So in this case how we solve this circuit, we use superposition theorem. We ignore one input at a time and consider the output for one input signal. So total V out is equal to V out due to the first input and plus V out due to the second input. We use superposition theorem. Now this is equal to V1 R2 by R1. I am just writing the expression from the lecture note, you can refer to that, to R4 plus R3 by R3, and for inverting terminal it is negative, so this is minus V2 R4 by R3. Okay, so you can see that if we apply voltage here, that will be V1 R2 by R1 plus R2 using voltage divider loop theorem at this point. And if we don't consider V2 here, for a applied voltage V1 into R2 by R1 plus R2, we will get, for non-inverting configuration, this is the gain, which is similar to 1 plus R4 by R3, so 1 plus R4 by R3. So that is due to the inverting non-inverting terminal input, and this is due to the inverting terminal input. Okay, now if R1 is equal to R3 and R2 is equal to R4, so V out will be equal to V1 R4 by R3 minus V2 R4 by R3. That means V1 minus V2 R4 by R3. Okay, so in this case this is the gain for this differential amplifier. So so this are the three configuration, the three ways we can do the amplification, and why differential amplifier. In case of some differential input we can get, so for example in case of thermocouple the output is the differential output, so in that case for amplification this configuration can be used, and for other in other cases we can use a non-inverting and inverting amplifier or any other amplifier. This is amplification is in open. So these are these circuits. Another topic that was also discussed, instrumentation amplifier. I'm not discussing again that, because these are the basic circuit, and if you know that, if you know how to solve different voltages and current at different nodes in different loop, then we'll finally find out the final expression. Okay. Next topic was filter. So we have different types of filter. First one is low pass filter. So what is the frequency response of a low pass filter? So this is frequency or omega, f or omega you can take, and this is the response which is denoted by h of j omega. For ideal low pass filter, it will pass all the frequency components which is below certain cutoff frequency, and it will block the higher frequencies. For high pass filter, the response is kind of opposite, so this is h j omega and this is omega, so the response is something like this. This is the cutoff frequency. Another is band pass filter. So in band pass filter, a band of frequency is allowed to pass. So this is omega, so this is h of j omega, and it will allow to pass some frequency, say some f1 to f2. Case of band stop filter, it will not allow certain frequency to pass. F1, F2. Now their filters can be active filters or passive filters. In case of passive filters, there will be no gain. It will only do the filtering action. So this gain here, this will be equal to 1. Whatever input we are giving, it will give the same output. Say, like if we apply some voltage, it will give the same voltage, ideally at least. So that is for passive filters. In case of active filters, we can make the circuit using some active component which will give some gain. So that will be that gain. So this will be say A. That is basically like that. So that is like filtering and amplification at the same time. Now basic low pass filter circuit is a basic passive low pass filter, so which is an RC circuit. So this is R and this is C. So this is a capacitor. Okay. This is R and this is V0. This is the applied voltage, that is V in. So this is ground. Now how we will get the transfer function or the input output characteristics. So input output characteristics mean V0 as by V in S. So in case of S domain, in frequency domain, and again we can use the voltage division rule. So V0 is equal to, so this is the voltage, so that is the voltage across this capacitor. So that will be whatever the current, that is multiplied by 1 by SC, which is the impedance of this capacitor. So capacitor is 1 by j omega C, right, which is equal to 1 by SC. I am not writing the current part because that cancel out, because V in is equal to, so V in is this, we can use KVL, Kirchhoff's voltage law, and law in this loop. So V in is equal to current in this loop plus which is multiplied by R plus of 1 by SC. Okay. Again that current will get cancelled. So this is the transfer function for a low pass filter, RC low pass filter. So this is equal to 1 by 1 plus RCS, and so magnitude will be, so not magnitude, so H of S, that is given by, we can write it as 1 plus S by 1 by RC. 1 by RC we can denote as 1 by omega naught, so 1 plus S by omega naught. Okay, so omega naught is known as pole 1 for this, because if we make in a transfer function expression, if we make the numerator is equal to 0, that gives us zeros for the transfer function. If we make the denominator is equal to 0, that gives us poles for the transfer function. Next, the magnitude H of j omega, that is given by this omega naught by, so S is equal to j omega, so magnitude we can calculate omega square plus omega naught square. From this expression you can see that when omega is equal to 0 or it approaches 0, omega is very small, that means frequency is very less, mode of H of j omega, that will become is almost equal to 1. And when omega tends to infinity, that means frequency is very high, H of j omega tends to 1 by infinity, that is 0, right? So that means if this is omega, this is mode of H of j omega. Initially we will have 1, then we will have almost 0. So that is like a low pass filter characteristic. So this is similar. So based on the transfer function also, we are saying that this circuit is for a low pass filter. Similarly, we can have high pass filter and other type of filter. Like in high pass filter, C will be here and R will be here in place of C. You can find out the transfer function and do the similar analysis and say that this gives a high pass kind of characteristics. And in case of band pass filter, we keep our R and C values in such a way that first we can connect a high pass filter and then we can connect a low pass filter, so overall so that we can get a band pass filter effect. Okay. In this course we have also studied generalized two-pole active filter. What is T configuration? So this is an op-amp, that is the active component. This is negative terminal, this is non-inverting terminal. This is the negative feedback, this is V0, and this is like this. So we input voltage is here, this is Y1, Y is admittance, this is the inverse of impedance, this, and this is Y4 and this is Y3. Okay. So for this kind of circuit, I am just writing the final expression that was discussed in the lecture series. So in this case, the transfer function is V0 by Vin, which is equal to which is the transfer function, and the expression is Y2 by 1 y2 y1 plus y1 plus y2 plus y3 to y4. So if you remember this expression, instead of y1 y2 y3 and y4, whatever component is given, you can put those values and find the gain of this filter. Find the gain of this filter at different frequencies. So by this kind of analysis, when frequency is equal to 0, when frequency tends to infinity, that means frequency is very high. So using this analysis, you can see what type of filter is this. Okay? So these were the topics, those were covered in this week. Next I will move to the questions. Is there any question before starting the problems? I hope there are people in the meeting. Yeah, so let's start the questions if there is no further questions from your side. So this question is on a voltage divider circuit. A thermistor of 10 kilo ohm is placed in a voltage divider circuit as given in the figure. So this is the thermistor, the value is 10 kilo ohm. If the input voltage is 5 volts, so V in is equal to 5 volt. The voltage across the thermistor, what is the value of V out? Okay, so this is like ground. There are few options. Option A is 1 volt, option B is 1.25 volt, option C is 1.5 volt, option D is 2 volt. So what is the correct answer? I am giving you some time so that you can give me the answer in the chat box. Okay. Yeah, this is a very simple calculation. You can just do like this. So for voltage divider circuit, V out is equal to, so in this case this will be our thermocouple or thermoresistor, whatever, our thermistor by R1 plus our thermistor, so which is multiplied by input voltage. So this is 10 by 30 plus 10, so 40 into 5, so this is equal to 1.25 volt. Okay. So the answer is B. So this is the second question. It's again similar. If instead of voltage current is given, so if instead of voltage the current is given, then you can use KCL. Say, let's go to the previous question. So what will be the current in this circuit? So this is 5 volt and the total resistance is, so current is 5 volt by 30 plus 10, so that is 40 kilo ohm. So this is volt. So this will be some milliampere. What is 30 by 4? What will be the value? 5 by 40, right? So 0.125, this will be milliampere, right? So instead of 5 volt, if in the question it will be given 0.125 milliampere is flowing through the circuit, right? So you can calculate what is the drop across 30 kilo ohm. So voltage drop across 30 kilo ohm will be R1, which will be equal to 0.125 milliampere into 30. So this is 3.75 volt, right? And voltage drop across our thermistor, that will be 0.125 into 10, right? So this is 1.25 volt. So instead of voltage, if current is given, so we'll get also the voltage across the thermistor is 1.25 volt, and when voltage is given, then also we are getting as 1.25 volt. So that is how, basically this is circuit analysis. That's how we will solve the question. I hope it is clear. Okay, do you have any more question? You can write in the chat box or unmute if you want. Okay, I hope there is no question. Assignment 8. First question is there. Okay, so in assignment 8 current is given. So this is the way to solve. I have not checked the assignment. I should not give you the assignment questions in the problem solving session. So, but you asked me how to solve it instead of voltage current is given. I have shown you the way how to solve it. Okay. So let's go to the next question. This is also again a voltage divider circuit. If two thermistors are placed in a voltage divider circuit as shown in figure 2, with input voltage Vin is equal to 20 volt and output voltage Vout is equal to 1.818 volt. So this Vout is 1.818 volt. The resistance of the thermistor, that is this resistance, in kilo ohm is, so there are few options. A is 1, B is 2, C is 1.5, D is 4. So what is the answer? Give me the answer in the chat box. So here instead of the resistance values, the voltage value is given. So the process is similar. You can use the same expression, the voltage divider rule. Okay. Tell me the answer. So there is only one unknown, everything else is known. We only don't know the resistance of the thermistor. So we can use the expression V in is equal to R2 by V out is equal to R2 by R1 plus R2 multiplied by V in. So using that formula we can get the resistance of the thermistor. So do I have an answer? Minus 1. So the resistance will not be negative. So maybe you have done some calculation mistake. So let me check. I have to also do the calculation. So the solutions. So the expression is V out is equal to R thermistor divided by R1 plus R thermistor is multiplied by V in, which is given in a question as V out is equal to 1.818 volt. So 1.818 volt, and our thermistor we don't know. V in is 20, R1 is 10 kilo ohm plus our thermistor. This is equal to 1.818 volt. So our thermistors will be equal to 1 kilo ohm, right? Because this 10 is in kilo ohm, 20 is in volt. So you can solve this, you'll get this. So the answer is A. This approximately equal to 1 kilo ohm. There is some decimal point. Okay, so 20 minus, I think when you do the shifted this from one side to another, then you must have done some mistake. That is why you are getting negative value, but the resistance will not be negative. It is a positive quantity. Okay. Okay. Let's go to the next question. So a temperature sensor is placed at R2 position. So this is R2 position, like in a normal voltage divider circuit. Then that notation is taken here. So this is a temperature sensor with an input voltage of 20 volt. So this is 20 volt. The variation in resistance for minimum temperature and maximum temperature is shown in this graph. So Minimum temperature is 10 degree Celsius, for which the value of this our sensor is 20 kilo ohm, and at 80 degrees Celsius, that is the maximum value of input for this sensor, it shows output of 200 kilo. So what is the range for the sensor? Between 80 degrees Celsius to 10 degrees Celsius. Okay, this is the input range and this is the output range. So range we have studied in first week. So this is one of the terminology that is associated with sensor, right? Okay, so uh, the output voltage V across the sensor for minimum temperature and maximum temperature. What will be the value? So there are few options. Option A is for minimum temperature it is 10 volt, and for maximum temperature it is 18.18 volt. Option B is 11 and 10. Option C is 8 and 9. Option D is 12 and 20. What is the correct answer? Again, I am giving you a couple of minutes to solve this question. You can tell me the answer in the chat box. So do I have any answer? Okay, let me do this. So this is again voltage divider circuit. So the expression is V out is equal to R2 by R1 plus R2 multiplied by V in, right? So when the output voltage is when the sensor is at minimum temperature, in that case R2 will be 20 kilo ohm, and when the sensor is at maximum temperature, the R2 will be 200 kilo ohm. So just by looking at the formula, we can say that when R2 is high, the output voltage will be high. So that means the output resistance V out will be more at higher temperature. So by looking at the options, straight away we can say that option B is not correct. In this case, for minimum temperature the output is maximum, so which cannot be true, right? So what will be the output voltage for minimum temperature and maximum temperature? So at minimum temperature, output is so R2 is equal to 20 kilo ohm, right? So V out will be equal to 20 by, what is this value? This is also 20, so this is 40 multiplied by 20, so this will be 10 volt. Okay. And at maximum temperature, R2 is equal to 200 kilo ohm, so V out will be equal to 200 by 220 into 20, so this will be 18.18. So our answer is A. Now there are few terms we discussed in first or second week. So the range for this sensor, what is the range for the sensor? This is between 20 degrees Celsius to 80 degrees Celsius. What is the sensitivity for the sensor? Can you tell me the sensitivity for this sensor with proper unit? Just do a calculation like delta output by delta input. So what is the output for this sensor? The output is basically the change in resistance, but we are getting the output as a change in voltage as V out, and the input is temperature. So the output, the sensitivity will be in the unit of voltage per degree Celsius. So what is the sensitivity? That is not given in the question. I'm just asking, adding from my side. So what is the sensitivity for this sensor? by 7. So the sensitivity is equal to delta output, change in output by change in input. So in this case, say let's consider at higher temperature, the output is 18.18 minus 10 volt, or we can say this is the slope. Okay, so this is temperature versus R2. We can have a similar graph for temperature versus V out, so that the slope will give us the sensitivity. So this will be 80 minus 10 degrees Celsius, so this will be 18.18 minus 10 divided by 70, so this is 0.1168 volt per degree Celsius. You can do a calculation from your side. If instead of 20 kilo ohm, if some other resistance value is given, what is the input output maximum and minimum input and output voltage, and what is the sensitivity. Now remember that we typically want higher sensitivity for our sensor, So based on that, what is R1 value you should take, that will give us more sensitivity, that you can see. Okay, some
Excuse me,
words.
madam. I have a doubt.
Yes,
So
ask.
normally, when we have such type of calibration curves,
Mm-hmm.
this curve is drawn between temperature on the x-axis and resistance on the y-axis. When we say resistivity, it is slope of the curve. It's a straight line curve. So slope means we can say delta R divided by delta temperature, correct? No, we have determined delta V by delta temperature. That's what I couldn't understand.
So for a single sensor, yes, that the output is change in resistance, and we will calculate the change in resistance by change in temperature. But we are
Yes.
connecting it in a circuit, and our overall output is a voltage signal. Say, suppose if you don't know what is inside of the circuit, it is like a packaged, say, sensor. In a packaged sensor, it may not be like a simple only that electrode or only the sensor material. There can be other circuit part also. Finally you are getting the output as a voltage, say, because most sensors are electronic circuits, so the output is in a voltage form. So in that case I'm saying that the sensitivities change in voltage by change in temperature. Now why I have given this example, I wanted to show you that based on the R1 value, your input, your output voltage will be different in different cases. Say in this case, you are designing a whole sensor system, and you are deciding R1, what should be the R1 value. So it's not the only sensor part you are not designing, you are also designing the circuit part. You are designing a whole sensor system. So typically if you are giving 20-volt input, so you want that it should vary, like it should have a good range, for output voltage. Now that will depend on the range, output range of the sensor, as well as on R1 value. So sensitivity, if you are designing the whole sensor, you are making like a whole package of it, and you are giving it to someone else, to some customer, then what the customer will see, the customer will see that the sensitivity is the output, how the voltage is changing when the temperature is changing. So that is from the design perspective, what should you take the value of R1, so that you will get a good range of output voltage. So just for that, so simply so if the question is not it is not a circuit question, it is like simple sensor question. Whatever, if the question is given us to calculate sensitivity, anyway that voltage divider circuit part will not be given. In that case you can do the calculation for sensitivities delta R by delta T. But if the circuit is given, if you want to decide what R1 value should be a proper value for your sensor system, not just for the sensor, then you can do the calculation like this, delta V by delta T, and whatever it gives like a good range of output voltage, that you can decide like what should be your R1 value based on that. I hope it is clear. Yes, you are right. Sensitivity, we normally consider whatever the output of the sensor. In this case, I am just calculating the output of the whole sensor system, so that if it is like a packaged system, what is the sensitivity, right? So if you remember, if you are present in first few weeks, I have given one data sheet for a MOS based gas sensor. Now in that case also, we will get the output voltage. It's like a packaged system. In many cases we get output voltage, even though it is a resistive type sensor. Inside of it, the change is in resistance, but we apply input voltage to in this case like V in, so that we can operate the sensor, because we have to apply some power, some energy, so that the sensor will operate, and we take output as a voltage output. I hope it is clear.
Yes, ma'am.
Okay. So we can go to the next question. So this is on Western bridge circuit. A thermistor is connected at one arm of a Western bridge circuit as given in this figure. If the bridge is balanced, the resistance value in kilo ohm for thermistor is. So what is this value? RT. The options are, so the options are in kilo ohm. This is 10. This is 100. This is option C is 150. Option D is 200. It is the answer. So it's good that I am getting some answers for this session at least. So given in the question just given that it is a balanced bridge, right? So in this case, for balanced bridge, the condition is that R1 is R1 by R2 is equal to R3 by R4. So for this case, R4 is equal to RT. So one thermistor is connected here. So this is 100K by 100 to 150. This is 50. So 1 by 2 and R4 is equal to 100 kilo ohm. Okay. So the answer is B. So by we can use like a simple voltage divider circuit also instead of a Western bridge. Why we use a Western bridge circuit? Say if there is some variation due to environmental parameter that will affect all of these four resistors, not only the thermistor. That will be cancelled out. That environmental effect is cancelled out in case of a Western bridge circuit. You can do a calculation like say due to some environmental change, the resistance values of all these resistors increases by say 1 kilo ohm. So this is 101 kilo ohm, this is 201 kilo ohm. So the bridge will be still balanced even if that condition that variation is, so it will not be exactly equal for all the resistors that increase in resistance, but you can say that the overall ratio that will be uh, in such a way that the bridge will be still balanced if it is not due to some uh, change in the variation in the input signal. So any other variation will be cancelled out, that actually affects like that will affect all of these resistors, and overall the effects will be cancelled out. So that is the advantage of a western based circuit. And we often use western based circuit to make to find the calibration curve in case of a resistive sensor, again because that will give us more accurate result. Go to this next question, question 5. So in a circuit given in this figure, if the temperature of the thermistor changes from 25 degrees Celsius to 30 degrees Celsius on application of heat, then resistance changes from 80 kilo ohm to 100 kilo ohm respectively. And due to this, value R3 is raised by 5 kilo ohm. The value of R3 for which the bridge is balanced. So these are the options. So what is the correct answer?
Value for R1, R2, and RT.
Well, RT is given at 25 degrees Celsius, it is 80 kilo ohm, and 30 degrees Celsius, it is 100 kilo ohm. The value of this uh, thermistor. R1 and R2 value actually you don't need. You can write down the equation for conditions for balanced
Oh,
bridge. You will see that those we can cancel out. So try it by yourself. If not, I will anyway share the answer.
okay. Thank you.
So you can write the expression at 25 degrees Celsius and 30 degrees Celsius, and from that you will get the value of R3. is the correct answer. Let me solve this also. So the condition for balanced breeze is R1 by R2 is equal to R3 by R4. For this case it is RT, the resistance of the thermistor. Now at 25 degrees Celsius the bridge is balanced. So R1 by R2 is equal to R3 by, at 25 degrees Celsius it is 80 kilo ohm, right? Now see, as the temperature increases from 25 degrees Celsius to 30 degrees Celsius, so this temperature increase is not due to input signal. This is due to, say, the temperature in which the temperature in the room in which the bridge is kept, that temperature ranges. It increased to 30 degrees Celsius. So that is affecting all of these resistors. That is affecting R3 also, and the resistance of R3 is changed to 5 changed by raised by 5 kilo ohm due to this temperature increase. Now remember, in this case the thermistor is not measuring any temperature of any object, right? So this is the overall change. So in that case also the breeze will be balanced. As I mentioned that for western breeze any environmental effect will be nullified. So the bridge is still balanced. Okay, that is the condition given in the question also. So the temperature range 5 degrees Celsius increase, that is affecting all of these resistors. So at 30 degrees Celsius also the bridge will be balanced. It will be some different resistance value, say R dash, but R dash by R2, that ratio will be same. Okay, and this is equal to R3 plus 5 kilo ohm by this will be 100. Now again, as the question, the bridge is balanced, so we can say that this ratio and this ratio is same. That means our R3 by 80 will be equal to R3 plus 5 by 100. So this is 10 R3 minus 20, the unit is kilo ohm. So answer is A, 20 kilo ohm. So the resistance of R3 it changed from 20 kilo ohm to 25 kilo ohm as temperature increases from 25 degrees Celsius to 30 degrees Celsius. Similarly, that will affect R1 and R2 also. Overall the ratio is same, so that the bridge is balanced. So that due to the temperatures change inside the room or inside the environment where the western breeze is kept, that is nullified. The thermistor will only measure the temperature change due to any object. Okay. So I hope it is clear. Next question. Let me write down the next question. Which term is a what type of circuit? So what is the answer? It's a very simple question. Just write the answer. Right, this is a DC bridge. So our input voltage is DC and our output voltage is also DC. Can we apply high voltage to a western bridge? Maybe we can, but if we apply high voltage, then the current will also be high. So normal resistor, normal material that we use, that will not work. So we will need a high power resistor for that. Okay. And power dissipation bridge, anyway, if there is resistor, there is some power dissipation, not only in a bridge or any, like in any circuit. Okay, so this is not true. So it's a DC bridge. Let's go to the next question. So this question is on amplifier. So in an inverting amplifier, a thermistor of resistance 5 kilo ohm is placed in the feedback part. So that is the feedback resistor. The value of output voltage V of the inverting amplifier is, so what is the value? So these are involved. So this is an op-amp circuit. So the configuration of this circuit is an inverting amplifier. So you already know what is the gain for an inverting amplifier, and the input voltage is given, which is a DC volt in this case. It can be an AC signal also for an amplifier. The input can be anything. So what is the value of the output voltage? Minus 40. So for inverting amplifier, output voltage V out is equal to minus RF by R1. I remember as RF by R1. RF means the feedback resistor. So in this case, that will be R thermistor by R1 into V in. So this is minus 5k by 10k into 80. So this is minus 40 watt. So C. Okay, let me write down the question I have missed. So the question is, determine the output voltage the given amplifier. Condition is when V1 is equal to minus V2 is equal to 1 volt. Let me draw the amplifier. Let me draw the circuit, open circuit. So this is negative, positive. So it's a differential amplifier. This is the inverting terminal. V1 is applied here. So this is 100K. And the feedback resistor is 100K. So we apply the feedback in the inverting terminal, the negative terminal, to make our circuit stable. At the non-inverting terminal, we are applying voltage V2. This is 20K. This is also 20K. So what is the output voltage for this circuit? You can use KCL and KVL to solve this. Okay. Let me give you the options also. Option A is -2, everything is involved. B is -5, C is -7, D is -6. Okay, I hope that you have done the solve the question. Let me solve this also. So I will draw this again here, the circuit. This is the non-inverting terminal. So this is the non-inverting terminal. This is the inverting terminal. The applied voltage is here V1. This is 100K. This is also 100K. This is here V2. This 20K. This is 20K. The voltage here at this node, let me consider as V minus, and at this node this is as V plus. Okay. I always denote this as V minus and V plus. There people use different notation, don't get confused. This is the voltage at this node. Now what consideration we do, we take that the input impedance of an op-amp is very high. That means no current is drawing, the op-amp is not drawing any current, and the impedance at this position V minus and V plus both are same. Okay, so we consider that the condition is that it's not condition, it is the consideration we take. If we consider the input impedance is as very high, so that is, so V in minus, we consider this as virtual ground. Okay. So let's say the current here is some I1. I will use this loop. Okay, so here current I1 will be equal to V1 minus V minus by 100k. That same current is flowing here, that will be V minus minus V out by 100k. Okay. So V out V minus is equal to V1 plus V out by 2. So this is our one expression, and for this case I2 will be equal to V2 minus V plus by 20k. This is equal to V plus by 20k. This is 0. Okay. So V plus is equal to V2 by 2. Now these two are same, so we can say that V1 plus V out by 2 is equal to V2 by 2. So V out is equal to V2 minus V1. So the gain for this is equal to 1, kind of, you can say that this is a differential amplifier and V out is equal to V2 minus V1. Now in the question it is given V1 is equal to minus V2 is equal to 1 volt. So V out is equal to V2 is 1 minus 1, which is equal to, so did I done any mistakes? So V2 is equal to V2 is equal to minus 1. This is minus 1 minus, this is plus 1. Okay. So this is minus 2 volt. So our answer is A, minus 2 volt. So we have the formula for so this is like the differential amplifier we have. In this case you can put your values here also, you can see whether we get the same answer or not. There is no question. Let's move to the next question. So let me write down the question here. Balanced condition of a Western bridge is obtained when option A is there is no flow of current through galvanometer. B is the galvanometer reading is maximum. C is there is current flow. Through galvanometer. D is there is a voltage difference. Between galvanometer thermometer. So what is the answer? Again a very simple theoretical question. The answer will be so what is a galvanometer? Think you have seen a galvanometer in basic electrical lab maybe. Answer is A actually. So galvanometer is a device that measures electric current. So there will be a needle that will move either direction to say in which direction current is flowing, and basically like a analog kind of device. It will not show you a number. There will be like a what it is called knob kind of, not knob, but so it will deflect. Basically it will show how the current is flowing. Okay, so it measures both the like current, the value, and the direction of current, right? So in so what we do in case of a western breeze, we place the galvanometer here. So this will deflect. So if there is a deflection, that means there is a current, and the deflection direction, that will give us the direction of the current also. So if there is no current flowing through this, that means the voltage at this node and voltage at this node is same. There will be no current flowing through it. Then the galvanometer will not show any current, any deflection. Okay, so it is a measure for current, and in balanced condition the voltages are same, so there will be no current, so there will be no flow of current through the galvanometer. So that is the correct answer. that is why we connect this in series. Like we want to measure the current here, that is why we like place it like this. If we want to measure voltage, so we will place like a voltmeter like this. At these two terminal we will measure the voltage. We are placing here, that means we are measuring current. You know how we place an ammeter and a voltmeter in a circuit. So if we measure voltage across a resistor, we place it parallel to that resistor. If we want to measure the current through it, we will place the ammeter in series with the resistor. Okay, so the galvanometer, it measures current. We make the connections like this. So this is the next question. So in the given figure, current flowing through this 2 kilo ohm resistor, what is the value for this 2 kilo ohm resistor? So you can solve this circuit. What is the current through this resistor? The options are given as 4 milliampere, 6 milliampere, 5 milliampere or 8 milliampere. Do the calculation. Give me the answer in the chat box. Okay, let's see. I think we have solved this kind of question in the live sessions also. T1, that is 1000 degrees Celsius or 100? I think this should be 100, right? 01. Otherwise it is a very like bad like sensor. If it is 1000 degrees Celsius, then I think from calculation wise, it T2 will be accurate. Like this is like that will create a huge difference. If that is your question, you can check. So maybe that is why, as per NPTEL, the answer is that. Okay, so if it is 100, then yeah, then T1 is accurate. If so, you can again write in the Q&A if in your assignment mark is not given. The concerned person will get back to you. So I'm not checking the assignments. Whoever is checking, so they will get back to you. They generally like answer your questions in the Q&A part in the discussion forum we have. Okay. So you can write this, but please do this before the exam. Okay. Let's get back to this question. So anybody has the answer? So what is the current flowing through this 2 kilo ohm resistor? So let me do this. You can see here that this is a balanced bridge. So if this is R1, this is R2, this is R3, this is R4, right? So R1 by R2 is equal to 1 by 2, and R3 by R4 is also equal to 3 by 6, that is 1 by 2. So R1 by R2 is equal to R3 by R4. So this is a balanced bridge, right? Now we know that if it is a balanced bridge, if this is VA, voltage at this node, and voltage at this node is VB, then VAB is equal to 0. So if the voltage difference is 0, that means current flowing through this 10 kilo ohm resistor, that will be also equal to 0. So this means current through 10 kilo ohm resistor is equal to 0. There is no voltage difference, that means current is 0, right? As simple as that. So our circuit will be like this. We have some input voltage. There is R1, R2, R3, R4. Current is 0 means we can say that it is like an open circuit. In an open circuit, current is 0, right? So our equivalent circuit will be like this. And what is our input voltage? 12 volt. Now this 12 volt is across, so this circuit is like this, right? There is one resistor and another resistor, again this one resistor and another resistor. Okay, so this is the same circuit. This is 12 volt, R1, R2, R3, R4. So this 12 volt is across this R1 and R2. So what is the voltage across R2? So this voltage will be 12 volt multiplied by R2 by R1 plus R2. 12 volt. What is our R2 for which we want to calculate current? This is 2 kilo ohm and R1 is 1 kilo ohm. So this is 2, 1 plus 2. So this is 12 into 2 by 3. So this is 4. So this is 8 volt. So what is the answer? So this is okay. So this is volt. So that is the voltage across. I need not to calculate the voltage across it. The question is the current flowing through it. So what is the current flowing through it? That will be, so the total resistance here is, so say I1 current is flowing through this, so I1 is equal to 12 volt by total R1 plus R2, that is equal to 12 volt by 1 plus 2 kilo ohm, so this is 4 milliampere. Okay, so the current through this 2 kilo ohm resistor, that will also be equal to 4 kilo ohm, right? So 4 milliampere current is flowing through this path. Okay, so our answer is 4 milliampere. So the voltage across 2 kilo ohm resistor, that was not needed to calculate for this question. Just calculated. I did not read the question properly, but the current is 4 milliampere. I hope it is clear and there is no doubt. So okay, thank you everyone. We are almost out of time, so I hope that session was useful. I will stop the session now, and all the best for your exam. Thank you for joining the session.